to 15.6, or we're gonna skip the section 15.5 because it is covered in chapter 16 in more detail. Triple integral in rectangular coordinate. There's a nice section. Let's go. Okay, for the triple integral in rectangular coordinate, what it does is that it does two things, right? You can figure out the mass of the object, and you can figure the volume, right? Let me sketch out a solid E here. Let's say a simple solid E. The concept. Let's say this is the solid E, solid E. We can figure out the volume of this solid. You can take a sample volume. So you can do a sample volume right. See, this is a sample volume. It's change in x, change in y, change in z. So dx, dy, dz, meaning that well, we can figure out the volume of this by sum it all over the solid E, and volume will be triple integral over the solid E, 1 dx, dy, dz. Sometimes we have dy, dx, dz, so I'm gonna call this a general dv. The sample volume here is just gonna be a dv here. Because you can set it up in in many different ways. So as you can see, right, dv can be dy, dx, dz, dz, dy, dx. There are 6 different ways to set up dv. It can be dx, dy, or dz. You see, dx, dy, or dz. So once you pick one, for the second box, you don't have 2 choices. So for this one, 2 choices, because you already picked one in the left box. And next one, well, you don't have 1 choice left. Okay, so as you can see, well, it's 3 times 2 times 1. It's 3 times 2 times 1. A lot of people would see this as 3 factorial. That's dv right here. Okay, now if fxyz is the density of the solid E, then we get the mass. Mass is gonna be triple integral density times volume, and then we're gonna sum it up over the solid E. Okay, so we have 2 things here, right? One of them is the volume, the other one is the mass of solid E. That is what triple integrals are used for. From the theorem. It's the Fubini theorem. Same theorem as in double integral. To compute the volume of the solid, E bounded by the surfaces in the first octane. Yeah. In the order A, dv equal d z d y dx. B, dv equal to dy dx dz. C, dv is equal to dx dz and dy. Different projection is going to get us the different setup. Okay, remember it's in the first octane, so whatever you see on here is in the first octane. Z1 minus x squared. That is a paraboloid. You go from 1 right here and you go back. So you come this 1, right? And you back. It's a paraboloid. And then this paraboloid is gonna be cut by the plane. You got to be very careful, right? So this paraboloid, whatever it is right here, I'm gonna just draw another line right here. So you can, it's gonna be cut by the plane. So there's gonna be a plane y equal to 1 minus x, gonna cut it. One minus x gonna be the plane that go through here, gonna cut this paraboloid. Okay, so the plane is gonna cut this part of the paraboloid out, so it's gonna cut it out. I'm gonna have to get back here. And then it is on the first octane, so you can only go as much in here. And this is the plane here, it's gonna cut that paraboloid. See, a plane cut in the paraboloid. Cut it out. Can only be in the first octane, so here come the part of the paraboloid. Okay, as you can see, the projection of E onto the XY plane is going to be this one. This region D right here. The volume here is going to be integral, not the integral of 1 it's going to be z. So here come dz. Z is the height, so the height going to go from 0 to the paraboloid. 1 minus x squared. And then dy dx. So that means you got to set up the region D in dy dx. Draw region D here. It is better to view it like this, that x, y. X go 1, y go 1, so it's going to be right here. Region D. dA is dy dx. Y is from, x is from. Well, as you can see, y gonna go from 0 up to the line, right? The line here is the 1 minus x. So 0 to 1 minus x. And then x gonna go from 0 to 1. Right? dy dx 0 1 minus x 0 to 1. So there's the setup here, a different setup. B. So in B, I'm gonna just resketch the solid here. Here come the xz plane. It is the projection right here. Projection E onto xz plane. We're gonna get a region D. So here comes region D. Well, if you have trouble seeing this, sketch it out on a 2D. Here comes X. Here comes Z. So XZ is X equal 1, Z equal 1, and look like it's the parabola. It's upside down parabola. It's not a straight line, right? It's a parabola. So this one, no, we already know the parabola because it's just z equal 1 minus x squared. Huh? Okay. Now it's going to be doing a dA. The dA here is the, according to the problem, we want to do dx dz. So x is going to go from, and z is going to go from. If you solve for x here, then x is going to be you have plus or minus, right? Because there is x squared. But because it is on the right side, you're going to do only the plus. So x go from 0 to the curve. And then z is the outermost integral, so it's just going to be between two numbers, 0 and 1. So in this case, what would be the volume here? It's 1, 2, 3. Here come 1. It's dy. Where does y go from? Remember, y here is going to be the height of the solid. You got to look at it the other way. So as you can see, y, right, it go from 0 up to the plane, because that is where y go to. 0 to the plane. 0 is the projection of E onto the xz plane. So it go from the xz plane to the plane that is the plane y equal 1 minus x. The xz plane is 0. It's y equal 0 to y equal to 1 minus x. And then dx dz, luckily we did the setup here. 0 to 1 minus z square root and 0 to 1, comma c. Just have to resketch the solid E here that I can show you. Now we're gonna project it onto the YZ plane, right? YZ plane is this one. Let's see. Remember, it's gonna be cut off between these two. So if you push it, then you're gonna see that the YZ plane is gonna be cut in into different region. Right? Okay, so Y and Z, right? So Y equal 1, Z equal 1 is just a square right here. But this square region is cut up by this line right here. See, there is an intersection of the two curve. This intersection, right? See, everybody see this intersection, right? And that is this one. Yeah, what is this intersection here? Well, the intersection we can figure it out because one of them is the paraboloid z equal 1 minus x squared, and the other one is y equal 1 minus x, right? X squared, and I'm going to sub so z is 1 minus y squared. There's the 1 minus 1 is going to be gone, so minus 2y, so it's going to be 2y plus y squared, so it's going to be minus 2y, I mean y squared negative y squared minus plus 2y. I mean, let me just do 2y minus y squared here. Because I had to put a negative in front of the y square and put it in front negative, and this look good. This is the intersection. So as you can see, there's two different regions. Oh my god, d1 d2, or you can write or1 or 2, but I'm gonna do d1 d2. Okay, so region D1, of course, the DA is going to be, now we're going to do DZ, DY, right? Z is going to be between, and Y is going to be between, right? And then we also have a region D2. Of course, the dA has to be a dz dy because the projection is onto the YZ plane. Z is going to be between, Y is going to be between, from the curve, right? So that's the 2y minus y squared to the line z equal 1. And then y going to go from 0 to 1. Okay, so we take care of the region D1. Now for the region D2, z is going to go from 0 up to the curve. And then y going to go from 0 to 1. Here comes the volume here. 1, 2, 3. 1 dx dz dy. I'm just going to do the setup here, and then there's another 1, 2. Yeah, put it a little bit out so I can make more room. Okay, so we know one of them is region D1, the other one is region D2. I can fill it up, and then you guys can help me out with the X there. And the other one is the sketch out the intersection, right? And then you put it on here, and then you can see it a little bit clearer. I'm gonna put the intersection. You guys see this projection of the green curve onto this z equal to y minus y squared here. It's the intersection. So you can see D1 and D2, right? So in D1, it's gonna be from 0 to the paraboloid. And then for region D2, x equal to 0 to whatever the red plane is. That so x equal 1 minus y. Okay, and this finished the setup, guys.